We now turn our attention toward the main focus of this chapter, which is finding ways to estimate the resistance of a cell and the total capacity of a cell. In this section here, we're going to find a simple way to estimate cell resistance that is actually not bad. We'll find somewhat better ways of doing it also, but the simple way may be good enough in practice. But there is no such simple way to estimate capacity, and we really want to understand why that is. Why is it easy to estimate resistance, and why is it hard to estimate the total capacity of a battery cell? So let's look at this, and it can be summarized by looking at the sensitivity of the voltage measurement to a change in resistance versus the sensitivity of a voltage measurement to a change in capacity, and they are vastly different. What we're trying to do is, in a sense, see how observable the parameter of interest is in our setup, where we can measure current and voltage only. There's technical definitions of observability. I'm not quite sure this is the exact definition that we're using here. We are using something called sensitivity, exactly has the same kind of idea. But the idea overall is how easy is it to notice, to see, to observe a change in a resistance from just looking at the voltage of a cell. And that tells us why it's actually easy to estimate resistance but not capacity. Let's look at our equation for cell voltage in the ESC model. We could, of course, have the zero-state hysteresis term 2m0sk, which I've left out for simplicity because we don't always use it, but that doesn't actually change anything here in the analysis. We define a sensitivity of the voltage measurement to a change in resistance as, so the symbol here, S is for sensitivity. The subscript is the sensitivity of something, and then the superscript is to something, so sensitivity of voltage to resistance. And this is computed as the ratio of the resistance to the voltage multiplied by the derivative of voltage with respect to resistance. If you do unit analysis on this, you find out that the sensitivity is unitless, and a small value means that there's very little sensitivity, that, for example, voltage is not changed very much when resistance is changed, and a large value indicates that there is a lot of sensitivity. And you could imagine that a large value of sensitivity is going to mean that something is more observable. So this is just a scaling factor to kind of normalize things and get the units right. But this here says talks about how much the observation changes when the element I'm trying to observe indirectly changes. So a big value of sensitivity, easy to observe. Small value of sensitivity, difficult to observe. So R0 over Vk, that there just comes across directly. And then the derivative of voltage with respect to R0, the only place that R0 shows up is right here, and so I have minus Ik coming out of that derivative. So R0, not too large, maybe about 0.01, or maybe at minimum 1 milliohm. It's rare to see a cell with less than 1 milliohm resistance. In fact, I don't know that I have. It would be a very, very large cell. And then the cell voltage, I don't know, 3, maybe what would be the worst case would be a big value there. So maybe 4.2 volts. So you would get something on the order, on that whole quantity of 10 to the minus 4. And then multiplied, though, by current, negative current, but the magnitude is what really is most interesting here. And current can be very large. Current can be hundreds of amperes, perhaps. So overall, the sensitivity result, when I multiply this by current, maybe on the order of 10 to the minus 2. And that might not seem like a big number, but that's going to be a lot bigger than what we find for capacity. So this absolute sensitivity of voltage to resistance turns out to be pretty high. That means it's easy to see, so let's look at a very simple method for estimating R0 that works perhaps surprisingly well. What we do is we take the voltage of the cell at time k and say it's OCV plus hysteresis minus diffusion voltages minus I times R0. And we do the same thing at time k minus 1. And there we have it there. It has the same terms, but with different times, of course. And then we take these two equations and we subtract them. So V minus Vk gives me V minus V, so Vk minus Vk minus 1 gives me that. And then we notice we've got open circuit voltage Zk minus open circuit voltage Zk minus 1. Well, in 1 second or one time sample, even if I've got a huge amount of current, the state of charge isn't going to change an awful lot. Maybe at most by 1%, but that even would be quite surprising to happen in one time sample. Okay, so max of 1% state of charge change. The open circuit voltage function is usually pretty flat, maybe a millivolt or so per percent state of charge. So we're talking maximum change in that term maybe a millivolt. Pretty small. So we'll say it's about 0 if I subtract those two terms. Same kind of thought process for hysteresis. I'm changing the hysteresis state in a very, very small way when I pass current, just one time sample's worth of current. So the difference between those two values when I subtract them is almost 0. The resistor current for the diffusion states, again, very, very small change. However, I times R, that can be fairly large. So if I go from minus full current to plus full current, I've got 2 times I max times R0, for example. That would be possible, although I guess it's not a very likely event. So maybe a couple hundred amps multiplied by a few milliohms would certainly give me hundreds of millivolts, would not be impossible, and it might actually be likely to have a large number of millivolt change in that term. So this term dominates those terms most of the time. So we use that kind of reasoning to justify that from time step to time step, a change in voltage is mostly due to R0 times a change in current. It's not exactly equal to that, but it's mostly equal to that. So we could consider forming an estimate of R0 by taking this, Vk minus 1, and dividing by this, Ik minus 1 minus Ik. So delta V over delta I, in the correct sense, computes an estimate of resistance. There are a couple, you try this and you realize instantly that there are a few special cases. One of them is, suppose current doesn't change, and that happens when I'm resting a cell. It happens other times too, but if current doesn't change, I've got to divide by 0. Well, hopefully I have a 0 divided by 0, but again, not necessarily, because I'm oversimplifying the model here. So whenever I have a change in current of about 0, it turns out to work much better if we just don't update the resistance estimate. We use the last value that we had. We do this when the delta I is equal to 0. We also use it when absolute value of delta I is relatively small, because small changes in current don't produce huge changes in IR, and they do produce some changes in these other terms here, so these other terms might have more of an impact than they otherwise would, relatively speaking. And if there's noise on the current sensor, the noise would dominate if delta I is small, much more than it would if delta I is big. So we tend to find it works much better if we skip updates when delta I is small. And small is in quotes. You have to come up with some threshold. It's a design parameter that will be your value, your decision point. If delta I is bigger than some value, then you make an update, otherwise you don't. And we'll have a homework assignment where you play with this and get experience with this, and I think that will be helpful for your understanding. There's also the fact that the enhanced self-correcting cell model is not a perfect description of how the cell works. It's reasonable, but it's not perfect. So there's going to be inaccuracies in this resistance estimate simply due to the fact that the model is broken. Not broken, but the model isn't perfect. So we find that this estimate, if we plot it versus time, is quite noisy. A lot of randomness in it. It bounces around kind of in the vicinity of some value that is the true resistance, but it's not perfect. What we can do then is we could do a number of different things. Basically, we want to filter the estimates. One way of doing it is using a total least squares approach, and this is what we end up doing to find total capacity in the last half of this chapter. But that's a somewhat more complicated methodology. Probably the best result you're going to get is using total least squares. But you could also just do kind of an engineering approach and create a low-pass filter on the result. So I start out with my raw estimate of R0K from the previous page, and from that I create a filtered estimate where the filtered estimate is some value alpha times the previous filtered estimate plus 1 minus alpha times this new resistance estimate. This filter has unity DC gain, so it should not be biased. And the value of alpha gives me the bandwidth of the filter, and we usually choose alpha quite close to 1, something like maybe 0.99 or even 999 or even 9999, so that we really place a lot of emphasis on the old value versus the new value, but we still do allow some blending of this new value to be able to update the resistance. You'll, again, for your homework assignment, you will investigate different values of alpha and find what you think seems to work best. So this method is perhaps surprisingly good at its ability to get resistance estimates that are useful. There are still a couple of other considerations that we have to take into account. One of them is that resistance is a state of charge dependent variable, and one way of handling that might be to have a vector of different resistances versus state of charge, and when I'm within some state of charge range I adapt only the element in that particular box. That's a possibility that you could do that. Another is we actually find that this resistance estimate here, if alpha is not chosen to be too close to 1, is pretty adaptive, and it can keep up with a change in SOC. So you would actually find that the resistance would vary as time varies because SOC is also varying. So we don't necessarily need to do this unless we need some kind of a more permanent record of resistance versus SOC. Another consideration is that resistance is temperature dependent, and this Arrhenius equation that we saw last semester that we applied to physics-based quantities does a pretty reasonable job of modeling these cell-based quantities too, especially the resistance. So we could say that the true resistance is equal to a reference resistance at a reference temperature times EXP tuning factor, the activation energy, if you will, of 1 over Tref minus 1 over present temperature. You can find that does pretty well. It's an exponential shape of resistance versus temperature and resistance. Looks like that. If we are adapting somehow parameters versus time to try to change the reference temperature and the activation energy, the reference resistance and activation energy, and if we dwell at all temperatures more or less the same amount of time, that can work. But if I'm always operating in this temperature region, then small changes in measurements can maybe bias the curve in that region. In that region, the bias looks really small, but as we extrapolate to the less commonly entered regions, it can really bias the overall curve. So this is tricky. How do we estimate resistance as a function of temperature? I don't know that I've got a very good answer for you. Another possibility would be just to continuously update all the time just one number and have that value change versus, just as time changes, which means temperature is changing and SOC is changing. That will work while the pack is operating, but when you turn the pack off and you turn it back on again at a different temperature, that resistance value is no longer valid because temperature has changed, and the estimate will give you poor results until it's able to readapt to the present temperature. So you might consider, again, updating a matrix of resistances, SOC versus temperature, and wherever I'm dwelling right now, I update that resistance, and as that changes versus time, I update the different values in this matrix. And if I dwell at least somewhat in all of these bins in the matrix at different points in time, I should have a reasonable estimate of resistance over the whole operating range of this cell. So those are ideas more than a lot of advice of, oh, I've tried it and this works best. I've tried a number of these things and they all have their pros and cons. Maybe you'll be able to find one that works better than something I've suggested. So that is, we've looked at sensitivity of voltage to the resistance and found that it's fairly high, and that allowed us to come up with a simple way of estimating resistance. Now we look at sensitivity of voltage to total capacity, and it shows us that the total capacity estimation problem is quite difficult. Here we look at sensitivity of voltage to capacity in the same sense that we looked at before. It's going to be Q over V times dV by dQ. And so Q over V is just copied. And then the voltage equation is this one right there. So I've got open circuit voltage minus the diffusion voltages. Sorry, I probably should have written this as RJ, IRJ, comma K. That's how we've usually been doing it. I wrote it here as capacitor voltage instead of as the resistor voltage. Of course, they're in parallel, so it's the same. But I'll update that in the notes. And I notice I missed an M in the hysteresis, oh dear. So there's some updating to happen to this equation. In any case, we want to take the derivative of that equation with respect to capacity. And we look at the equation and we say, there is no capacity, it's not there. But be careful, we are taking a total derivative, it's not a partial derivative. So this is saying when capacity changes, it will have perhaps a direct effect on voltage. It doesn't, we see that here. But it may have an indirect effect on voltage because when capacity changes, it changes something else. And we do find that. So when I take derivative of I times R0 with respect to capacity, that's gone. There's no impact there. There's no impact there. However, we do see some impact here and here. So let's look at the first term. The total derivative of OCV with respect to capacity is by the chain rule. The partial derivative of OCV with respect to state of charge times the derivative of state of charge, total derivative of state of charge with respect to capacity. This says if I change SOC only and leave everything else fixed, how does OCV change? So we look at our OCV versus SOC figure. It looks like that. And then we look at the derivative of that, which usually looks something like this. And so this is OCV, and that's, well, no, it isn't at state of charge. This is dOCV by dSOC partial, and this is SOC. And so there is something there. It's not zero. However, in this part of the curve, which is where we operate most of the time, the slope is very small, and so the derivative is very small, and it's usually on the order of maybe 1 millivolt or a couple of millivolts per percent state of charge. So this derivative term here exists. It's positive, but it's small. Now I need to look at the other term here, the total derivative of SOC with respect to capacity. So here, the total derivative of SOC right now with respect to capacity, we look at the SOC equation. Zk equals Zk minus 1 minus eta k minus 1 I k minus 1 delta T over Q. So taking the total derivative term by term, total derivative of that term gives me this. The eta, not a function of capacity, the I not a function of capacity, delta T not a function of capacity. So those are constants. But then I've got derivative of 1 over Q by dQ, which is a function of the capacity, of course. The derivative here we evaluate using calculus. It's just minus 1 over Q squared, so I have a plus and a Q squared that shows up. And the first term is, notice that and that are the same thing at different time instants. So this is something that we would calculate recursively. We would initialize dz0 by dq equals something, and then we would update it if we wanted to compute the sensitivity with respect to time. And over time we would be able to get these new values here. So this first term that we can compute recursively grows when, you can see that. How does it grow? Well, it grows according to this equation. So the derivative increases when current is in the same direction for a long amount of time. If current is positive, then negative, positive, then negative, then what I'm adding each time step is in one direction, then another one, then the other, and so forth. And it doesn't. So this term that contributes to sensitivity stays about 0 or small. But if current is the same, then I'm basically accumulating through this. I'm integrating through this sensitivity. So for random IK, the term is about the same order of magnitude as the second term, which we could actually compute. But for non-random, then it can grow. So that tells us that if we want a high sensitivity of our voltage to capacity, I need to be charging for a long period of time or discharging for a long period of time. And this is motivation for, very often we do capacity updates when the vehicle is plugged in, because I'm going to be charging the battery pack for a long period of time. I've got a lot of control over the charging current and so forth, and over this long interval I can monitor how the voltage is changing in a fairly precise and controlled way, and that is useful for updating capacity. But if I have a vehicle or an application where I don't ever plug it in, I just have random charging, it turns out to be really hard to estimate capacity, because this term here doesn't grow, or this term, whichever one you want to look at, same thing, doesn't really grow. And this term here is kind of constant magnitude, and it can be positive or negative as current charges or discharges. Also, the second term, notice, has a 1 over t in it, And if my sample rate is 1 hertz, that's 1 over 3600. If my battery pack is a high capacity, maybe, I don't know, a 20 amp hour battery pack, well, that's 1 over 400. And even if current is fairly large, relatively speaking, it gets divided by this quantity, and I get a very, very small sensitivity contribution in the measured voltage due to the passage of current. So overall, this is our conclusion. Sensitivity of voltage to capacity through the open circuit voltage term in the output equation is very small. It's present, but it's very small. And it's probably dominated by measurement noise. So we would have to accumulate a lot of measurements in order to get to average out this measurement noise and try to get a good sensitivity by, as we said, charging for a long period of time or even discharging for a long period of time. That's why we can measure capacity in the lab pretty well, by the way, because in the lab we take a cell, we fully charge it, we fully discharge it, and we have complete control over long periods of time where hopefully we have very accurate measurement equipment and so forth, and we can estimate capacity there. But as I'm driving and my voltage is doing this, my current is doing that, and my voltage is doing whatever, very, very hard to estimate capacity. And that's just fundamental. That's just fundamental to the cell. It has nothing to do with the method by which you estimate capacity. This math is giving us ideas that some scenarios are going to make it easier to estimate capacity than other scenarios, but there's a fundamental limitation on our ability to estimate capacity just by how it shows up in voltage. If we look at the sensitivity of the hysteresis voltage to capacity, it's also very low, and especially for long charging and discharging, which helps us with OCV. It doesn't help us with hysteresis because hysteresis tends to a constant value, and in that case it's only in the transient parts where you might have some hope of estimating the capacity through hysteresis term, which is exactly the opposite as through the OCV term. So individual voltage measurements, one voltage measurement at a time, or maybe two consecutive voltage measurements, give us very little information regarding capacity. So somehow we have to combine many voltage measurements. Simple ideas like the one we use to estimate the series resistance just don't work. They don't work well. So in the rest of the chapter, we're going to look at two basic approaches. One of them is a Kalman filter based approach, and that builds on the material we saw last chapter, so there's not a huge amount of new learning, it's just a new application. So we'll spend a few sections looking at that, and those can work well because the Kalman filter is a recursive estimator, and so it does fold in past information into the present estimate of capacity. For this to work well, though, we really need to have quite clean estimates of state of charge from our filter. So I need to have the best state of charge estimate that I can have. If I don't, then the Kalman filter-based approach turns out to be biased, to have an offset in the estimate. And so in the last half of the chapter, we'll look at something called a total least squares approach, which is an optimal approach for estimating capacity. It's a little bit, well, it's quite different from the Kalman filter-based approach. If we use the absolute optimal version of total least squares, it turns out to be not especially computable. It has a lot of problems that way, but we look at an approximate solution that is easily computable, and probably even less computation required than the Kalman filter-based approach, and gives better results. So that's why we spend some time looking at that then.